Nuclear detonation safety began with the first 2 atomic bombs in the summer of 1945, the days of Fat Man and Little Boy.
On Tinian, Northfield, there were 4 great parallel runways. They ran nearly across the total width of the island at that point. Oftentimes, there were accidents such that you could see burning B-29s in the vicinity of the runways.
The Little Boy and the Nagasaki were not safe if we'd had an accident. If it dropped them, or if we'd crashed on takeoff from on Tinian, we would have wiped out part of the 20th Air Force. We'd have lost 400 B-29s and a lot of people. They were not safe. Well, the Nagasaki bomb, which was an implosion bomb, was built up by hand, and the plutonium core was inside the high explosive.
The bomb contained enough plutonium and was sufficiently close to being critical all by itself that there probably would have been some nuclear yield.
Little Boy, the enriched uranium gun-type device, and Fat Man, the more complex plutonium implosion system, posed serious nuclear safety challenges.
So one of the problems, of course, was to make weapons safe, and the only way we could do it was keep the fissile material separate from the assembly mechanism. Now, we didn't do that for Nagasaki. We just took off and hoped everything would be all right.
Both bombs were fully loaded with fissile material at takeoff. Nuclear safety consisted of a system of green and red plugs.
The principal safety measure in a loaded bomb, a bomb that was aboard the aircraft, was electrical safety.
The plugs essentially kept the circuits open from the power supply to the high explosive and its detonators.
In flight, before the bomber was pressurized at 8,000 feet, we took out green plugs and installed red plugs.
And with the arming plugs in, that connection was made. So there was that physical action that had to be taken aboard the aircraft before the bomb was released.
Wartime 1945 drove many hard decisions, including the first use of 2 atomic bombs on Japan, one untested and both unsafe in an accident.
From 1947 on through 1950, the Mark III bomb was the primary operational weapon. And this was a militarized version of a Fat Man.
It wasn't a bomb, it was a collection of parts that had to be assembled by a specially trained team.
And so all the problems that existed with the weapon delivered over Nagasaki also existed with the Mark III.
Meaning if some accident happened to it, you would have a nuclear yield. So one of the design criteria for the Mark IV and all later weapons was that the nuclear capsule would be separate.
The Mark IV was the first weapon to include a function we called in-flight insertion, which meant that the nuclear material in the form of a capsule could be moved along a track and put into the center of the weapon while it was on the way to the target.
The next stage was, instead of doing that manually, was to build within the weapon itself a mechanism that would have the capsule external to the explosive.
So Sandia developed an in-flight insertion mechanism, which the pilot could turn on a switch and the mechanism would insert the capsule inside of the high explosive assembly. The back end of the capsule, of course, had that piece of high explosive which made up the totality of the sphere.
The initial generation of nuclear weapons were capsule-type weapons. A separable nuclear capsule served the interests of absolute nuclear safety, and for a short time, it also provided the means of civilian control.
And in the very early days, civilian control of nuclear weapons meant civilian custody.
And when they had an exercise, the sirens would go off, and the gate between the two fields, so to speak, with the military on one side and the atomic energy and the fissile material on the other side, gate would be open, and there would be a transfer of material with receipts being signed.
Over time, though, that arrangement proved unworkable. The military argued that in a crisis, this would delay a nuclear response when hours might matter. In 1950, this problem came to a head.
The United Nations sent an army to Korea under a single command to hold the aggressors at bay. It was almost
Truman was petitioned by the Air Force of first the bombs and later the capsules for potential use in the Korean conflict.
As the war in Korea escalated and threatened to develop into a global conflict, President Truman approved the transfer of nuclear components to the U.S. Air Force based in Britain.
From the perspective of the Air Force, they did not enjoy the notion of not being allowed to deliver a nuclear weapon in time of war without the approval of this upstart civilian agency.
The idea that nuclear weapons were actually going to be part of, integrated into American security, created a tremendous tension between this idea of civilian control and the ability of the military to plan for nuclear strikes. Withholding authority from the military was ludicrous to a commander like Curtis LeMay.
There was tremendous pressure on the nuclear command and control system to shift from an never-oriented system to something that would be better able to respond in a crisis. And from that time on, the military had custody of nuclear weapons.
There was this romance, if I may use that expression, about nuclear weapons. It meant that the services, if they were to be relevant, which means getting funding from the administration and the Congress, had to be part of the charmed circle of nuclear capabilities. So the Army strove to acquire nuclear weapons. The Navy, in order to demonstrate its relevance in the period, equipped its carriers with nuclear weapons. And of course, the Air Force during that period was central to the buildup.
So every offensive capability they had to become nuclear. Everyone had to have one.
Now what happened in the early 50s, the specter of guided missiles entered the picture. And getting the missile to the target was a Department of Defense responsibility.
Department of Defense, for missiles and rockets, was responsible for the arming signals, the safety to be provided outside of that nuclear warhead, and the fusing signals to tell it when to fire.
A 1953 agreement carved out areas of responsibility between the DoD and the AEC.
We ended up having to very specifically define where the interfaces were between the AEC hardware and the DoD-supplied hardware.
The interface literally was a connector through which the signals passed to initiate the arming sequence in the warhead.
Sandia was becoming very concerned about supplying a warhead that just required an electrical input to detonate.
We're talking about delivering, let me call them, bare warheads to the services.
A bare warhead would be vulnerable to any stray or intentional voltages. And on the right pair of pins, it could cause the weapon to go off.
A massive nuclear weapons complex had taken shape in less than a decade, supported by an unbridled enthusiasm for all things nuclear. The 1953 Missile and Rockets Agreement was an addendum to a larger document spelling out AEC and DoD responsibilities for the complete life cycle of nuclear bombs and warheads. Soon, designers and engineers throughout the complex would discover and address the safety implications of this new generation of weapon systems.
Fall 1950. A fierce international war rips through a small country on the North Yellow Sea called Korea. Russia has successfully detonated an atomic bomb. We need to develop and produce a greater number and variety, and possibly even more powerful atomic weapons. Weapons tailored for specialized uses and targets.
The services wanted a nuclear weapon for every conceivable purpose.
In a report to the Joint Committee on Atomic Energy, tactical nuclear weapons represented the future. They promised a revolution in land war. They were the natural answer to the armed hordes of the Soviet Union, and their coming would immeasurably strengthen Western Europe's will to resist.
In the 1950s, we saw weapons added at the rate of about 3 different types per year. The growth was dictated largely by the capacity of the plants.
This is the mile-high city of Los Alamos, the atomic city. This is a modern pueblo created by the people of the United States as a research and development center for atomic weapons.
Nuclear weapons were the product of a demonstration of a brand new capability by Los Alamos and the adoption of that by the military planners.
And whatever we could do, they liked. Didn't matter what we suggested, they liked it. They were very good customers.
The early weapons were maintenance and intensive and required preparation time.
The Mark VII used perhaps 20 different complicated testers. We at Sandia felt that these procedures were causing more damage to the weapon than they were finding.
In 1952, the Mark VII bomb was one of the first fighter-delivered nuclear weapons. But by the late 1950s, the Air Force adopted a strike-ready posture, and capsule-type weapons were deemed inconsistent with this new operational readiness.
What they were giving to the military in terms of hardware was burdensome.
Hidden under this security cover is the most destructive force ever devised by man, an atomic bomb.
Well, clearly the idea of having the military having to assemble a bomb didn't at all work with the 5-minute alert concept.
And that was the driver, one of the drivers for wooden bombs.
In 1954, weapon designers envisioned a nuclear bomb that would provide operational simplicity or woodenness, in which the required operational, maintenance, and safety care approaches that of a piece of pine.
The concept was to try to come up with something, a bomb that could withstand years in storage and be instantly available for military use. In the earliest weapons, there was a lead-acid battery used, which took 3 days to prepare. Characteristics of this type made it very difficult for the military to remain on alert.
One of the developments that enabled the wooden bomb was the advent of thermal batteries. These were batteries that were completely inert until torched, if you will, by an electrical signal.
It was a dual-pronged approach. One, go to thermal batteries, become more test independent, and at the same time, I think independently, the physics labs were trying to move towards a physics package design that allowed them to put the nuclear material inside the explosive itself.
Los Alamos' new sealed pit primary was proof tested at Yucca Flats.
Sealed pit technology was a revolution. And it allowed essentially immediate availability.
With the sealed pit, it was a package deal, so to speak, and in order for the military to be effective, they had a control of the whole system. We were always worried about what we call accidental nuclear detonation. And when we had the sealed pit, we had to develop at the same time the concept of inherently one-point safe systems.
Duncan McDougall at Los Alamos conceived of this notion that if you ignited the high explosive at a point, it would consume itself.
Meaning that if in an accident, the high explosive were detonated at one point, it would not lead to a nuclear event.
The calculations were done mainly by a man named Bob Osborne, and the best we could do and guarantee with certainty was 1 chance in 1 million, that there'd be no yield greater than 4 pounds. And I had based this 4 pounds criteria on the basis that there might be an accident on a ship, and the nuclear radiation from such an event could be contained within one of the compartments on the ship.
The new sealed pit primaries prompted a change in the safety emphasis, from controlling the nuclear material to controlling the electrical energy. In early 1957, there were 14 new weapon systems in the pipeline, all based on Los Alamos' sealed pit design. One of these 14 systems was the W-49, a warhead mated with the earliest intercontinental and intermediate-range ballistic missiles.
The 49 was the first of the warheads intended for reentry vehicles that was small enough to be practical in a reasonable size missile and still have a large yield. Early on, the Atomic Energy Commission provided the nuclear explosive package and the fire set.
And the Department of Defense was responsible for the fusing system, which would deliver the proper signals to the warhead at the appropriate time to cause them to detonate.
Arming and fusing signals, together with the source of power, were supplied to the warhead by the missile.
To be compatible with DoD systems, you had to have an interface where the two came together, and that was the form of an ordinary connector with pins and sockets. I can remember in the military as a young lieutenant, my favorite tool was a voltometer because now I could troubleshoot the circuits in a logical way. It was just a simple matter of removing a plastic cap for weather protection and doing these tests.
The concern grew about a friendly fiddler or someone just mistakenly connecting a voltage up and getting a very bad result.
A single individual with information about schematics, which were widely available, and a battery in a lunchbox could detonate a nuclear weapon. This was not good.
The W-49 was not considered to be an especially dangerous system or different than any in the past. It was just the time to begin stepping up to the plate, change the situation that existed in the past of not having some kind of environmental protection in the Sandia AEC hardware.
I took it upon myself to authorize the design modification, if you will, to provide a first-generation environmental sensing device, in this case, an accelerometer.
No longer could you come up to the interface and put signals that would pass on down. It was a positive block until sometime in the deployment to the target, an environment was sensed that would allow that signal to pass. So there was an open switch, literally, the first open switch for safety.
Sandia would address this problem and oversee the installation of environmental sensing devices in bombs and warheads throughout the stockpile. Comprehensive stockpile safety began with the work of the influential Klee Committee report that spawned nearly 70 safety studies, culminating in a Department of Defense directive establishing formal safety standards for nuclear weapon design.
The Klee Committee clearly influenced the future direction of safety, creating the positive measures. The positive measure concept was incredibly powerful in the sense of saying we need to see something that's engineered specifically for safety. Safety really means availability. If you have a safe weapon, you can deploy it anywhere in the world and not put the public at risk.
By 1960, SAC was running an operation called Positive Control Launch to ensure the survivability of its bombers. This deployment of nuclear-armed B-52s would present new challenges for detonation safety.
An atomic bomb breaks loose from a mounting shackle in a B-47 jet over Florence, South Carolina, plummets to Earth, causing a sensational freak accident.
A Mark VI gravity bomb, accidentally dropped by an Air Force bomber, was of the earliest generation of capsule-type weapons. No nuclear capsule was aboard the bomber or installed in the weapon, and damage was limited to the detonation of the bomb's high explosive. The accident in March 1958 was the 13th involving air-delivered nuclear weapons. 6 months later, the Strategic Air Command would begin to test its continuous airborne alert mission. During the next 10 years, the Air Force would be plagued by accidents involving air-delivered nuclear weapons.
We were running some fairly high-risk operations. We were flying a large number of airplanes and during most of the 50s and into the 60s, continuously with nuclear weapons on board.
Hardware wears out. Things happen. And the Air Force caught the brunt of those issues.
Their focus was reliability, readiness, not accident safety.
In the late 1950s, Strategic Air Command began to carry sealed pit weapons, where the bomb was loaded up and always ready to go. Accidents involving sealed pit weapons would represent a manifold change in the risks of an accidental nuclear detonation. One of the earliest accidents involving airborne alert bombers occurred in January 1961 over Goldsboro, North Carolina.
It was a normal flight. It had just refueled with a KC-135 tanker. The boom operator on the KC-135 told the pilot that he noticed a pink fluid leaking out of the right wing of the airplane. Pilot disengaged, radioed in to SAC headquarters to say that he had a fuel leak. B-52s are a big flying fuel tank, and it's necessary so that they stay in the air. You've got to transfer fuel from the center body of the aircraft out to the wings. During one of these transfer operations, the right wing of the airplane physically ripped off. All of a sudden, now that weapon system is free. As the weapon dropped, power was now coming on, and the arming rods had been pulled, the barrel switches began to operate. The next thing in the timing sequence was for the parachute to deploy. When it hit the ground, it tried to fire.
There was still one safety device that had not operated, and that one safety device was the pre-arming switch, which is operated normally by a 28-volt signal.
Some people can say, hey, the bomb worked exactly like designed. Others can say, all but one switch operated, and that one switch prevented the nuclear detonation.
Unfortunately, there have been 30-some incidents where the ready safe switch was operated inadvertently. We're fortunate that the weapons involved at Goldsboro were not suffering from that same malady.
The accidents provided valuable information to AEC weapon designers. At Sandia, improvements were made in later generation pre-arming ready-safe switches. Unfortunately, there was no shortage of new data as the accidents continued. In January 1966, a mid-air collision over southern Spain raised international alarm.
The accident over Palomares, I think, was significant because of the scattering of plutonium on foreign soil. It had incredible press coverage of that arena and incredible negotiation between the U.S. government and the Spanish government with respect to the level of cleanup.
We wound up buying up a lot of tomato fields over there. After the accidents, many things became more evident to us and in fact to the world, because it was such a stage that they could see now.
The U.S. was embarrassed in a world community.
In early 1966, Strategic Air Command's Airborne Alert Mission, codenamed Chrome Dome, had been operational for 5 years.
Robert McNamara, who had been skeptical about whether the Chrome Dome operation was still necessary, wanted to put an end to it. Strategic Air Command was able to argue that that was a very rare event, it won't happen again, we've instituted operational procedures so that there won't be another accident of that sort. Unfortunately, they were wrong. B-52 on an airborne alert mission had a fire on board. The aircraft crew evacuated the aircraft. The plane then drifted without anyone on board, landing 7 miles outside the base, blowing up on the ice.
When the plane went down, it tended to melt the ice and then plate the thing, so you had a layer of ice over the top of the contamination. They had about 39 inches of ice when we got there, and of course they wanted to preserve all that ice they could for cleanup.
And whenever there's an accident, political authorities quite rightly say, have we gotten this right? Sometimes they've said that accident was not so damaging, it was a rare event and we can live with it. Other times they've said this was unacceptable.
These were fairly serious incidents. They were international incidents. And we had to come to some grips that perhaps we needed to adjust our posture.
And so we recognized that, hey, there's a high consequence event that can happen here. It's unacceptable. We have to deal with it. Out of that came what we call the Wolski criteria.
Karl Wolski, assistant to the Secretary of Defense Atomic Energy, initiated a reappraisal of nuclear detonation safety in the wake of the 1966 Palomares accident. But the 1968 accident at the Thule Air Base in Greenland became a catalyst for change.
The Wolski criteria that was put out in 1968 gave 2 clear definitions of levels of safety for nuclear weapons. The key factor was, given an accident, the likelihood of a nuclear detonation should be less than 1 in a million.
And 1 in a billion for just sitting there, normal environments. Something that the U.S. public in Congress and in the White House would understand, so we put a number on the level of safety.
These accidents showed that you can have fire followed by crush followed by electrical insult. A sequence of environments happening that you may at one time deem not to be credible, but nature has a way of voting.
Mother Nature's a devious adversary.
That's my personal view. Accidents are going to happen.
Given the accident, how will the hardware, how will the weapon system respond?
Will it go the way I say it will, predict it will, designed it will?
Versus a system that's highly complex, where it would not always fail predictably. So given that, we have developed a set of design principles from which we implement nuclear safety from the start into the weapon system design.
In response to the 1968 Wolski criteria, all three AEC laboratories intensified their focus on safety. Los Alamos would introduce insensitive high explosives. Livermore would develop fire-resistant pit technology, and Sandia would establish the enduring concept of enhanced nuclear detonation safety. Underlying all of these developments was a new understanding, indeed acceptance, of the probability of an accident.
I think where we fool ourselves if we think we've thought of all the ways that accidents might occur. The key thing for weapon safety is, given the accident, prevent the ill.
The nuclear accidents of the 1960s shared common themes. They all exposed the weapon to extreme environmental insult, fire, crush, and electrical shock. By 1972, Sandia's Independent Safety Assessment Group would assemble evidence upsetting traditional understandings, findings that would forever shatter the image of order conveyed to the designer by circuit diagrams and layouts.
Creating an independent safety group, I think, was absolutely vital and probably the key to why improvements were made.
Jack Howard was strongly involved in encouraging an advanced development activity in a safety organization separate from the warhead developers.
If the design groups have somebody muttering constantly in their ear saying, always, shouldn't there be somebody muttering, never?
What we need is a simplifying notion. So a small group was convened, and I isolated them and said, I don't want you worrying about day-to-day problems. Think this through.
And so what I asked for Bill, well, we want to need some time, some months, to go in and really try to now understand safety from a more fundamental viewpoint.
In 1968, Sandia designers asked, are we doing what we need to be doing for abnormal environment safety? Their approach was twofold: analyze the safety features of existing weapons and expose those components to severe abnormal environments.
The feeling at the time was things are pretty good. We've had a lot of accidents. We've never had a detonation.
People didn't, at that time, understand much about accidents.
Well, I think early on they assumed that things could fail in such a way that the system wouldn't work.
Key assumptions at the time held that an electrical fault to ground will dud the weapon, and that circuits and connectors will open up in an accident. Early detonation safety was achieved by employing ready-safe switches, environmental sensing devices like accelerometers, by using printed circuit boards and cable isolation to ensure the electrical integrity of the safety system.
And safety was really on isolating the wires from the power coming in to pre-arm the weapon, for example, from the charging circuits.
The early weapons were put together in such a way that this could all happen in the junction box. And in the junction box, you have the inputs and outputs together on a wiring board.
Wiring boards with all of these different paths in it, and then you maintain a separation between those paths, and then you put an insulative material, electrical insulation, over the top of it. You've made a cocoon around these items, and they're going to be safe.
But those were safety features in essentially normal environments.
All of this hardware was developed in a vintage when abnormal environment was not considered.
Once you start involving fire and unusual environments in that, then you start shorting out cables and coming up with circuits that can cause a degradation of the safety that you've built into the bomb.
After several years of intensive torturing of existing hardware, the study group found that the response was not predictable.
When test objects were subjected to thermal insult by an electrical fault, the charred organic material would cease to insulate and now conduct electrical current.
Conduction. And you can get conduction to many circuits in there.
In other words, you're creating new electrical paths within your wiring board, and those electrical paths could go through and arm the weapon system and fire it.
Charred insulation or melted solder would not simply open up a safety circuit and dud the weapon, but would cause unpredictable propagating damage. Further still, there was no technical basis for this model of safety practiced among designers.
Their assessment and their analysis was not based on fact, was not based on testing.
And this was a great eureka, if you will, in the safety arena, that we need an approach that allows for unpredictability.
When you really start to build a safe nuclear weapon, your first task should be to create a barrier system to isolate the critical power from your critical arming and firing circuit. So you need a barrier.
Barrierize those. And then you don't have to worry about what's happening outside.
It was a simplifying notion because now you didn't have to study all the ways things could go wrong, so it made the problem manageable.
In 1971, the Independent Safety Assessment Group proposed a radical redesign of all weapon electrical systems, beginning with the concept of an exclusion region,
where we isolate energy sources from critical nuclear weapon detonation elements to prevent a nuclear detonation. Exclusion barriers, which are walls that contain capacitor discharge units, are the energy sources that can light off the detonators for the system.
But you don't have an operational weapon. To make an operational weapon, then you've got to essentially put a hole in the barrier to put in the arming energy when you need it.
And we did this through what we call strong links, which are basically switching devices, so you keep this electrical energy off these elements like detonators.
We used 2 strong links. We were unwilling to assume that we had the skills necessary to devise a single switch that would give us 1 in a million protection.
Each one has to be independently effective to avoid some common mode failure. What you don't want is a common mode where, with the same kind of input, both devices would fail.
So we used 2 designed differently.
And then the third thing you had to do is to make sure your strong links were not susceptible to just common everyday voltages.
Some signal that would not normally be postulated during an accident.
An unambiguous indication of human intent is what it needs to open that gate.
That unique signal that was incompatible with all of the common voltages and the voltages as they may be modified by the abnormal environment.
Ultimately, the features of enhanced nuclear detonation safety were designed to prevent nuclear yield in the face of severe abnormal environments.
But eventually everything, so now we'll make it fail in a predictable way.
We deliberately designed some parts of the firing system to fail irreversibly, such as a high voltage capacitor.
And so what you'd like to do is have something become inoperable. And so that was the concept of a weak link. And so you started co-locating, the strong links with the weak links, so that as the environmental insult started to heat the weapon, you would have the weak link become inoperable before the strong link became ineffective. And so out of that work came the basic principles that have really stood up for years: isolation, inoperability, and incompatibility. Some people have suggested a fourth principle of independence.
That makes you safe. So that was the great breakthrough, I think, that Stan Spray and his staff came up with.
Enhanced nuclear detonation safety with strong links and weak links and meet the criteria of extreme safety. That was a clean, simple, and most efficient way in which anything that failed for whatever reason would neuter the system.
Thinking back, that's kind of an obvious thing, maybe. But we didn't have it until these folks invented it. A requirement to change the design specifications so that you have more safety.
I think it was just a gradual, natural evolution, because we were always concerned about safety of the devices, especially as the numbers of them kept increasing and the deployment was pretty much worldwide.
In the northwest corner of South Vietnam rests the small valley of Khe Sanh. The siege is on. The North Vietnamese launch a massive artillery attack. U.S. commanders predict a major North Vietnamese offensive just before the Lunar New Year on January 30th.
In late January 1968, the Johnson White House was consumed with the war in Vietnam. Coming just days before the North Vietnamese Tet Offensive, the Thule nuclear accident was almost a distraction. McNamara called for an immediate halt to SAC's Airborne Alert program.
Chrome Dome is canceled because of the embarrassment and the costs involved with having a second nuclear accident. And yet, the interplay between the warning system and the offensive capability that Chrome Dome led us to have wasn't contemplated at the time. Indeed, when the B-52 crashed outside of Thule, senior officials in the Pentagon really didn't know that the reason why it was so close to Thule was because it was on this special Thule monitor mission. The B-52s on the Airborne Alert also had a second mission, which was to look down at American air defense radars to make sure that they were working properly.
One of the concerns was that the Russians could take out one of the radars as a means of hiding the follow-on attack prior to a major launch on the United States. But what happens if the airplane that crashed, the nuclear weapons on board went off and destroyed the radar?
There was a potential for an accident to occur that could have cascaded into a false warning. This kind of unusual interplay between an offensive nuclear system being kept up in the air, a defensive warning system, and the command and control never had been thought through. It was too unlikely an event.
A low probability event that you'd have both the airplane crashing and the nuclear weapons going off within range of the radar to destroy it. But it wasn't infinitesimally small.
Fortunately, the one-point safety system that had been placed on those bombs worked, but exceedingly rare events occur all the time.
Generation exercises were a mainstay of SAC long after Thule happened because they were no longer flying Chrome Dome, but they still wanted to maintain operational readiness.
We used to load the bombers up with a full load of bombs and pull them on the end of the runway and go to take off fire, roll down the runway. And then chop the fire and go off the runway on the high-speed taxiway and taxi back to the alert area. Because we wanted that realism. We wanted assurance right up to pull back the yoke and take off that the crews could do everything.
These were oftentimes referred to as elephant walks. So they continued to do all of the things of handling the bombs, bringing them from the storage area, installing them on the clip-ins, putting them up on the bombers, and everything short of flying them.
These could be fully loaded airplanes, fully loaded with fuel. And so it was quite taxing on the brakes to do this. And a number of situations occurred where the aircraft actually caught on fire because of hot brakes. SAC was continually putting themselves and the weapons at risk conducting these ground alert operations.
It was generally well accepted by both the civilians and the military, the civilians in the AC and the military, that we had to have a posture that was survivable. In the interest of survivability, we have accepted some risks. Two departments have worked together very well in trying to mitigate those risks.
Positive measures mitigating the safety risks of nuclear weapons were formally established in 1960. And from the beginning, nuclear detonation safety was conceived of as a shared responsibility.
It's the principal responsibility of the Department of Defense to assure that the abnormal environments don't occur very often. In fact, at a diminishingly low level. But it is the laboratory's responsibility to assure that given an accident, that will not be allowed to progress to a nuclear detonation.
In late 1970, 2 years after the Sandia Safety Study Group began its work, the weak-link, strong-link concepts were formally briefed to the DoD. But acceptance of this new standard for safety design came slowly.
Some of the discoveries were actually disbelieved by a number of designers.
They wanted to believe their nice, orderly world, the one they were trained in and raised in. This is the way electrical circuits behave. So we arranged to make a display called the Burned Board Briefing.
And people were seeing actual examples of what could happen. They were not just seeing view graphs and words about what might happen. They were seeing hardware about this, this could happen.
The idea of a burned board briefing originated with Bob Purifoy. After leading Sandia's successful design effort for the Navy, Purifoy became Director of Weapon Development and undertook a complete review of the stockpile.
I quickly became concerned about electrical system designs that would tolerate severe accidents. Those bombs that used high voltage, thermally activated batteries.
So all of those weapons could possibly be armed in the case of a fire that set off the high voltage thermal battery.
The electrical systems of greatest concern were those of air-delivered weapons on alert, those loaded up during SAC's generation exercises. In spring 1974, Sandia Vice President Glenn Fowler briefed the lab's concerns to the Division of Military Application at AEC headquarters.
There was some reluctance on their part to greet that with any enthusiasm. The DoD felt, I think, that what they needed was more warfighting capability. They had enough safety.
Fowler and Purifoy decided to go on record with their concerns.
Glenn's memo expressed that these weapons should be upgraded with modern safety features or retired.
Right away, people were indignant that the labs would blow the whistle on themselves.
Words coming from the designers themselves can't easily be dismissed
as possibly false. And that caused no end of hysteria in Washington.
The burned board briefing was arranged as a demonstration for key Washington decision makers. Among the first to receive the briefing was the Assistant to the Secretary of Defense for Atomic Energy, Don Cotter. A former Sandian, Cotter found the briefing a sobering experience. In May 1975, he issued a directive for a joint safety evaluation of the entire stockpile.
Give the DoD credit. Once they decided to go do the stockpile review, they went at it with, enthusiasm, and I think with a real hard look, not only this time at the weapon, but at the weapon system.
Beginning in the summer of 1975, joint technical working groups were formed to evaluate each category of weapon and weapon system against modern safety standards.
This was a joint review process. We had people from the laboratories and from the Department of Defense working together as a team to review the system.
Strategic air-delivered weapon systems on alert were given first priority. The conclusion of the safety studies in spring 1977 coincided with more than a decade of advanced development work, yielding the first air-delivered weapon to fully incorporate enhanced electrical safety, the B-61 Mod 5.
The B-61 got its start in the early to middle 60s. Everybody on the team would get a pep talk that we were working on the Cadillac of all bombs. The design architecture of the system was such that it allowed for a continuing set of improvements for achieving improved safety, particularly as well as improved use control.
This inherent safety and security would in time make its way through the rest of the modern stockpile. The B-61 established a modular architecture for nuclear weapons.
The firing set and the original 61s eventually were replaced with firing sets in roughly the same volume that had modern nuclear safety features and capabilities, all integrated into the firing set.
And that's why packaging becomes so important when you're first laying out the design of a nuclear weapon. You can clearly put in strong links and weak links and have them totally ineffective if they're quite some distance apart. And that's the reason we co-locate and put them basically within the firing system itself.
The modernization of the weapon systems didn't happen overnight. There were units that were out there that had no modern safety associated with them. It became more and more apparent that we need to review our entire stockpile.
Improvements to older air-delivered systems began in 1979, a time when East-West relations were descending to new lows. During the 1980s, strategic and conventional arsenals expanded on both sides. A global anti-nuclear protest movement emerged. Nuclear arms control efforts were re-established, and a nuclear accident galvanized world opinion.
Mr. Gorbachev, tear down this wall.
By the end of the decade, sweeping political changes had overtaken well-laid plans for weapon system modernization. An era had ended when older systems were routinely replaced with new and safer designs. Ensuring the always and the never of nuclear weapons would at once become more public and more challenging.